worry. Like, we can catch up anytime.
I'll tell her that.
Whenever she's ready, okay?
That's not in her nature, but
That's beautiful. I'm going to say her goodbye.
I'm gonna see more. I'm sorry.
No, I can see it.
I know. I kind of want to see too.
Where are the cigars?
You don't need those cigars, that's true. We did have a little Super Bowl party in the hospital room.
So is she home now? She's home?
Still home, yeah, we got home yesterday, so.
He was going to Super Bowl Sunday.
What's that?
He was going to Super Bowl Sunday.
I was born on Saturday morning.
Yeah, on Thursday, she's like, I'm going to bring the reporter on Tuesday. I'm like, Joanna, I don't think you're there on Tuesday.
She thought she was.
Tuesday's a long time from now.
Yeah. She was.
Only Joanna would worry about regression with the newborn.
Thank you.
Of course. Of course.
Only Joanna was like, I should go in and Kara was like,
Yeah, of course. Of course. I would have sent her home, don't worry.
And congratulations to her too. Tell her.
I'll tell her. Thanks, guys.
How was your weekend? Less eventful than hers, huh? Should I ask you guys to go and like turn those values into z-scores and do the regression? Did anybody see anything interesting?
About the z-scores?
No, not necessarily about the z-scores, but you remember what was the correlation? What did we look at? We looked at.
0.66.
What did we look at? We were looking at. I forget the two variables we were looking at.
X and Y.
X and Y.
Yeah.
X and Y, and then the first time I had you compute a correlation between X and Y, and what did you get?
0.82.
You got a 0.8, we all got a 0.82, right? All right, and then you also got an estimate for the intercept and then the slope, right? And what was the intercept and the slope? This was like 3, and I think 0.5, something like that. Yeah, and then I had you turn each of those data sets into z-scores, right? So you had a distribution of x, z of x's, and a distribution of y of x's, right? Did you correlate those two scores? And what did you get? You got a. So then you went and you said the correlation between the z of x and the z of y is 0.82, right? Did you do a regression?
Yeah.
Did you notice anything? Maybe you'll notice now. Did you get an intercept? Was it a tiny, tiny number?
0. Yeah.
It was 0. And what was the slope? I bet it was 0.82. Look at the board. See if you see anything.
It's all the same.
It's all the same.
Thank you.
It's all the same. It's all the same. One way we can estimate this intercept or the slope is that we can do r, x, y, the standard deviation y divided by the standard deviation of x, right? That's another way we can do it. So if we turn our values into z-scores, what happens to the standard deviation of x and y? They're 1. So this cancels out and this becomes the slope. And that's because it's all the same. It's all the same. Got it? Okay. All right. And then I asked you to think about what's the interpretation of this value. Right? How do we interpret this value? Because now it's no longer for 1 unit change in x. We see a corresponding change in y now, right? What is x? What is the unit of measurement in x? You've turned them into z-scores. So now how do I interpret this? For every one standard deviation unit increase in x, I see this standard deviation unit change in y. Right? This becomes important because what happens if we have variables of different magnitude and we have multiple regression, we have several predictors? What's going to happen is that the raw coefficients are going to be of all different magnitudes, and then it's difficult to answer the question, well, what's important? to answer that question, you have to put them all on the same metric, and you know how to put them all on the same metric, and that's turn them into z-scores. And then you can interpret these as standardized estimates, right? You had that look on your face, so I want to address that look.
This is just my look.
Okay.
Well, so what does this offer you that the other doesn't?
Okay, so that's good. So this tells us the equation using the raw units, the raw values, allows us to make that prediction in the raw unit metric.
Right.
Right? When we standardize the values, we get what are called beta coefficients. That's what we refer to them as beta coefficients, or standardized regression coefficients. So if I have bivariate data, one thing that we know is that the slope will equal the correlation, right? So we know that. But the other thing is that the interpretation of the coefficient changes. Instead of for every one unit change in x, we expect a half unit change in y. Here, for every 1 unit change in the z of x, which is a standard deviation, is for every 1 standard deviation increase in x, we expect a 0.82 standard deviation increase in y. So this becomes important when we eventually extend our model out to look something like this. You know, we have a b1, x1 plus a b2, x2, dot, 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 dot. You know, and then we have, you know, Burger King in here somewhere for the b of the k. Right, where we have many predictors, and you want to say, well, what's the strongest predictor? Right? Let's say that this becomes like sex, right? And we're going to score that as a 0, 1. That's going to have small variance. Whereas, let's say B2 might be age, and that might take on the values of 18 to, I don't know, 100. So that's going to have more variance than this. Right? And let's say that BK comes into, I don't know, something with a lot of variability in it, like brain size. Brain size is going to be measured in hundreds of millions of voxels from an MRI, where, you know, we can have standard deviations of 100 million voxels. So the standard deviation of 100 million voxels will probably lead to incredibly tiny beta coefficients relative to a fairly large coefficient of age or sex. So comparing one coefficient on the raw data directly is kind of meaningless. So how do we compare them? We standardize them. Okay.
Is there anything about the sum of those z-scores that tells you something, like if you're way above 1?
Well, the sum of the z-scores, well, let's look at the z-scores, right? So we have to understand the z-score, so I'm going to write down some things. Right, that's the formula for a z-score, right? Right? And what's the numerator of the z-score? It's a residual, and we know that the sum of the residuals will always be 0, right? And a z-score is a residual. So they will also sum to 0. So the sum of the z-scores will always be 0. Okay? Does anybody have any insight as to why the slope, or I'm sorry, the intercept would be 0 when you standardize the data for this bivariate regression model?
Basically, the intercept is the mean of x and the mean of y, right?
Exactly. Right? So if we were to draw the data, right, and this for y, and let's assume for the sake of argument that y is normally distributed, and this is x, and x is normally distributed. Well, the z of x, the mean of that is going to be what? That's going to be 0. And the z of y, the mean of that is going to be what? So if that's 0, 0, the point's going to go through the origin there. Make sense?
Sorry, I think I asked my question wrong. I meant the b's or the betas. Like if you have if you do your univariate correlations and you do all of them, and then you turn them all into z-score, do you standardize all of them? and then you add them up, and they're like greater than 1, does that mean there's
No,
one?
no, no, because what we have, when we get to the multiple regression, what we would then talk about is something called a linear combination. So it's not, I'm not going to add up my z's, I'm going to add up the products of the coefficient times my z. And that becomes the predicted value of y. So it's not just the sum of the z's, it's the sum of the product of the coefficients and my z's. It gives me my expected value. Okay? All right. We good? All right, so in a couple of weeks, we have gone through univariate statistics, bivariate statistics, which leads us to the next step, which would be what? Multivariable statistics. Okay, so sometimes you're going to just trust me and say, and just accept that all this stuff is the same. And we just sort of gone through this exercise, empirically have demonstrated that all this stuff is the same. We talked about throwing a rock into a pond, right? Right, we had this example where I had some thing and then I had some other thing, right? And we talk about the circles representing the variability of the two variables, of the respective variables. So I'm going to call this top variable my y variable, and I'm going to call this variable my x1 variable. Okay. So let's talk about what happens when we include 3 or more variables in the set of equations. Okay. So there's a couple of things that could happen. So to be clear, my y variable is my outcome. This is the thing that I'm interested in measuring. My x variable are going to be my predictors or my intervention. Okay? So this is my outcome. These are my predictors. My x variables will be my predictors. Okay? So again, to review the concept that we did last week, we talk about this section here, the intersection. How would we interpret that?
It's the area where x1 is having some impact on y.
Right, where the shared variance. Remember we wrote down the shared variance. We did sums of squares total equals the sums of squares of our model plus the sums of squares of error. And we did that exercise where we did all the y hats and we did all that subtraction and all that stuff. And if we said that if these are parts of the whole, then if I do sums of squares model divided by sums of squares total, this is our r squared. This really is a proportion. It's a proportion of total variance explained, right? It really is. This white area, this non-shaded area, becomes the amount of variability in y that we haven't explained. That's the error portion. That's the coefficient of alienation, right? All right. Okay, so let's think about it this way. What happens, has anybody ever read an article or heard language where a researcher or a statistician talks about controlling for a variable in a non-experimental study? Does anybody know what that means? Where you just sort of say, okay, they've controlled for it. That's okay. Okay. Here's what they mean in a non-experimental study. So now we're going to create a third variable. We're going to add a third variable into the mix. And I'm going to call this variable x2. Okay? So without putting any numeric values to these things, let's do the following. I'm going to say the area A represents the amount of variance in y that these two variables don't predict. So A would be the sums of squares total, sums of square error. Okay? Okay. So A, so let's write this down. So the sums of squares total will be the area A plus B plus C plus D. Does that make sense? That represents the whole area of Y. So if I ignored x2, if x2 didn't exist, right, we would say, I'm going to write this as r y x sub 1, r squared, is going to equal CD over A, B, C, D. Does that make sense? You with me? Making sense? Okay. And if I were to write down the squared, the coefficient of determination between x2 and y, how would I write that?
BC over ABCD.
That's right. Anybody see a problem, or can anybody intuit a problem here?
Is it the area of C? You're double counting for it essentially.
Well, it could be an issue of double counting it. Or think about it another way. Remember in the first day of class we talked about theory building, right? And then I think the last things I talked about on Thursday was this idea of we're going to maybe think about variables a little bit differently. Okay, so does anybody have a project in mind that they're going to do, or that they're interested in doing, or they are doing? And can you talk about it a little bit? Nobody's doing any projects? Okay. So let's pretend for a minute that we're doing some policy research. Right? What's our outcome of interest in our policy research? Make it up.
Quality of life.
Quality of life. Oh, so health-related quality, thank you, of life. Okay, and what do we think is going to be related to quality of life? So this becomes our dependent variable, or our criterion, or our outcome. And what we're going to say is, what is quality of life a function of? What goes into quality of life?
Pain, age.
Pain, age. What else?
Comorbidities.
Say again?
Comorbidities.
Comorbidities. What else?
Functional status.
Functional status. What else?
Income.
Income. What else?
Family support.
Support. Now we're thinking like scientists. Keep them coming.
Gender, race.
Gender. Absolutely. Race. Ethnicity, which is different from race. Right? What else? Anything else?
Time spent seeing doctors.
Okay. Time spent. I bet there's an inverse relationship there with medical community. What else?
Housing status.
Housing status. Come on, keep going. Because we're building a model now, right? Right, you're going to control for all of these things. What else do you want to control for if you're interested in studying health related? Depression, cognitive function. What else?
Geography.
So geography. What else? Anything else?
Weather.
Okay. season, maybe? Right, season. What else?
Time spent in your house.
Okay.
Versus nursing home and hospital.
Time
Not in your house versus.
spent at home. Okay.
Yeah.
You can be a misanthrope and be really happy being alone. Right? Okay, all right. Good enough for now? Okay, so if we were to think about this set of variables, I bet with just a little bit of thought, we could begin to group these variables together somehow, some way, in some meaningful way. So let's start doing that. Let's start with an easy one, age. What kind of variable would that be? It's continuous. It's a demographic variable, right? Can you set any policy or deliver an intervention that can affect age, one's current age, right? You can't randomly assign someone to an age. You can't do that, right? So,
we can make things more accessible for people of certain ages.
but you can't change people's age, right? Right? You can't make a policy that would affect someone's age, right? So let's think about things that we may not be able to affect, no matter how much we try. In income, right? The government's doing such a good job with that. Gender, race, ethnicity. While we're at it, let's differentiate gender from sex. Okay? Anything else? Okay, so these are interesting. These are variables. Season, oh, we can't do season, but is season a demographic variable? That actually might be another kind of variable. So let's think about it. So these are things that no policy can affect, right? So what we might be able to want to do is say, you know what? I don't want my intervention. I'm going to put another variable in here called treatment. I don't know what that is, but it's some treatment, some intervention designed to affect quality of life. Okay? So what I might do, what I might be interested in doing is, the speaker's hissing in my ear. What I might be interested in doing is removing the effect of these variables from my outcome. Okay? Why would I be interested in possibly removing the effect of these variables from my outcome before I looked at the effect of my treatment?
It tells you what effect the treatment has independent of the other variables.
That's right. That's exactly right. And maybe not even independently, right? Because what about this C region here in the Venn diagram? Is it possible that people of different ages and races and ethnicity could have better access to my intervention? No, that doesn't happen all the time, right? We don't want, right? So it's possible that if I think of these purple underlined things, I can still think of them as X2. Even though it's not one variable, it's a set of variables, but I can think of them as one set of variables. Let's call them demography, right? So what I might want to do is say, you know what? I'm not going to give let's say X1 is my treatment variable, X2 is my demography variable. You know what? I can't give treatment credit for these variables. Right? There's no way my intervention or my policy can affect these things. So I'm not going to take credit for it. So what I can do is I can hold them constant. You with me? Okay. So here's what I might do to hold them constant. There's a couple of options that I have available. I can do what's called a partial correlation. okay, a partial correlation. So let's say, for the sake of argument, let's just label these things. Okay, so it's not just x, y, and x, right? Now we have labels to these things, makes it a little more concrete. What I might be able to do is I might be able to hold demography constant by literally subtracting out the effect of demography from both the outcome and my variable of interest, right? You know how to do that already, believe it or not. So let me write the equation as to how I would do that. I would regress x1 onto x2. Right? I would regress it. So I would do a bivariate regression in this case. Right? Then what I would do is I would take my x1 observed, right? This looks familiar, minus x1I hat. You've done this before. What's that? An observed value minus an expected value is a residual. You've done this before. So then I would get this quantity. So this quantity would equal D plus G. Right? Because I have literally subtracted out C and F from X2.
Can you just explain the first step again?
This,
Yeah.
I'm not saying they're equal. Correct. This is regressing. This is regression.
Right.
So I'm going to regress X1 from X2. What I mean by that is I want to predict X1 from X2. Right? Which should yield CF. Right? CF is this, is the expected value. So if I subtract CF from X1, what do I get? DG. So what I really have left over is I'm going to call this X1 prime. Because it's no longer X1. It's kind of X1, but it's not X1. Right? And what happens is that this X prime, X1 prime, has a correlation. Anybody know what the correlation of this X1 prime would be with X2? It would be 0. Not approximately 0. It would be 0. Because I have literally removed the variability in X1 that can be predicted from X2. I've residualized the variable. Maybe you've heard people talk that way. So when we say we've held something constant, what we're doing is we are literally subtracting the effect or the shared variance of that thing that we're holding constant out of the equation. Right? So a partial correlation does that to both variables. So what would happen is then I would regress y onto x2. Right? I would do that just like I did with x1. And then I would get yi minus yi hat, which is a what? Residual. That's a residual. So in this case, what would be left over? AD. A plus D. I'm going to call that yi prime. It's no longer y. Because I have literally removed B and C from the outcome. And then, yeah, go ahead.
Could you go back to how you get from regressing x1 on x2 to x1I minus?
Yeah, okay, so this is me being sloppy. It's a regression, so
Yeah.
if I were to really write this, I would be x1I beta 0, beta 1, x2 sub I plus epsilon I.
And how does that get you the residual below?
How does that get me here?
Yeah.
So then I would get x1I minus beta 0 plus beta 1 x2 sub I equals epsilon I. All right, this is the regression equation I get from predicting x1 from x2. This is this. Right, because this is my expected value of x1 sub I. This and this are the same thing. Right? You know how to do this. You already know how to do this. Okay? You got it? Okay. Good question. All right. So then what I want to do is, now that I have removed the effect of x2, what I really have is something that looks like this. This is hard. Like that, kind of. A, D, G. Yeah, got it? So then now I have, so basically what I'm going to do is correlate the residuals. I can correlate the residuals. So the partial correlation between y, x1, 2 is going to the squared is going to be d over a plus d. This is a p for partial. Does that make sense? We have literally subtracted the effect of x2 from both of the variables. That's what we mean statistically by saying holding something constant. Statistically. Make sense?
When you're taking out the effect of x2, so you're just putting the x2 in parentheses there, and then the initial...
Yeah, because the x2 tells me what I've held constant. Yeah. Yes.
So what happened to G from the residual term?
G is still here. But I'm interested in what is the area between y prime and x1 prime. Well, that's still here, but what I'm interested in is this. Right?
You have to do that for every variable that you want to...
We could, but regression does this for us. But before we get into the regression, I want to give a concept of what regression is doing for us. Okay? This is what multiple regression does for us. Okay? Now, this is what we observe when we have observational studies. Right? So I can think of examples where I would see this. So how would you describe that relationship?
So x1 and x2 both impact the variance of y, but independently. They don't there's no CF, there's no...
Right, there's no intersection between the predictors. Can anybody think of any examples where that would likely happen? This is a randomized design, a randomized clinical trial. Right? Because if X1 is treatment, what is the process that gives rise to this variable treatment?
And then the sign.
Chance, lottery. Right? So if it's random, by definition, can anything correlate with something that's random? No. But in any given clinical trial, is it possible for these two things to correlate?
Possible.
It's possible, right? And if we measured enough of these X2s, it's plausible that I could find maybe for every 20 variables that I include as a predictor, one of them would correlate. Let's see here, 1 over 20 is what? It's 5%. Where'd that come from? Alpha, right? But what gave rise to that? Is that a true relationship? No. Because by design, by the structure of the design of my study, X1 and X2, if I were to repeat that study design over and over and over again, the average correlation would be 0. Whereas in an observational study, if I were to repeat my social experiment, I'm not going to call it an experiment. When I say experiment, I mean randomized trial. If I were to repeat my social study over and over and over again, is it possible, is it likely that the real correlation between demography and my treatment would not be 0? Yeah, we call that a selection bias. That by definition is a selection bias. Okay? So what would happen if I remove the effect of X2 from this set of equations? Let's do A, B's, and C's. So now, sums of squares of y is going to equal A plus B plus C. So what happens when I residualize X2 from the set of from that set of data? Does the relationship of C, does the magnitude of C change?
No.
The absolute value of C doesn't change. But what happens when I look at the relationship between X1 and Y after I remove X2? The absolute value doesn't change, but what does change? The relative value changes. So what I'm doing in a randomized experiment by using blocking techniques or a covariate or some other variable in the equation, what I'm doing is I'm not controlling for things. This concept of including predictors from clinical trial data was designed by Fisher, that guy, that cranky old Brit. He designed these kinds of study designs not to control for things, but to minimize variance. So if I remove B from Y, I have minimized the variability of Y, which increases the relative size of C, which will do what? It will jack up the association between X1 and Y, making it easier for you to see that relationship between treatment and the outcome. So this is what, whenever I can decrease the variability in my study, we call that efficiency. Right? So you may hear statisticians and trialists talking about efficient study designs. Efficient study designs means I'm decreasing the variability, making it easier to see a difference. Okay? I'm going to leave this up here for a second. Go back to this. So I can write down right all over my hands. And I'm going to leave that there. Right? This is a partial squared correlation, squared correlation between x1 and y holding x2 constant. Now imagine trying to explain to a policymaker or your grandmother, except for Lisa's grandmother, who was really bright, a residualized y. What do you mean that's the effect of X, treatment on some residualized outcome? How do you residualize an outcome? What the hell does that mean? You lose an intuitive meaning of the statistic. I mean, unless you understand what's going on. Right? Because if you were to look at this, how would you explain what a partial correlation is between two variables? It's the truly unique variance. The truly unique variance between the variables. Right? That's how you could explain it. Right? What the hell does that mean? Truly unique variance. So what we can come up with next that has a little bit more of an intuitive meaning is something called a semi-partial correlation, which is going to be, in this case, D divided by A plus B plus C plus D again. All right, so looking at the semi-partial, semi means what? Half. So I'm only going to remove the effect of x2 from only half of the equation. So a semi-partial correlation would be the effect of, or the correlation between y and x prime. So what I'm going to do for the semi-partial correlation is I'm going to remove the effect of x2 only from x, but I'm going to leave y completely intact. Does that make sense? And in fact, that's what multiple regression does. That's what multiple regression does.
Is that to prevent an increase in the relative size?
No, what it does is it leaves y completely intact, and then by doing so, the semi-partial correlation, this statistic, has a more intuitive interpretation. Intuitive, right? I'm up here talking about intuitive. So try this on for size.
The denominator is the whole of
Yes, yes. So if the denominator of y stays the same, how would I interpret D? Just look at it. What is D?
The independent effect of x1 on y given everything else.
Yeah, right? On y, not y prime, but y.
Yeah.
Right?
Yeah.
So I can also think about, that's really good. Another way I can think about it is, it's the effect of x1 on my outcome above and beyond everything else in the equation. Or we can think about it, another way to talk about it is, what is the incremental r squared of adding x1 into the model? Okay? So let's get back to our list of variables here. So we have the concept of demography. And we're going to, what is that? That's age, income, gender, sex, race, ethnicity. And that, okay? So I might think of those as, those are my control variables. No matter what I do, I can't have a policy that will affect someone's age at the time I take the measurement, unless I want to make fudge the data. Bad policy. Not a good policy. Right? I can think of other things too, right? Let me get another colored marker. Are there other variables in here that I could probably group together in a meaningful way?
Pain and comorbid conditions.
Okay, now we're talking. Pain, comorbidity,
Time spent with the
doc, depression, functional status. Housing could be that's a demographic variable too, right? Let's do that.
If housing is in geography.
Okay, fine. Okay. What else?
That's a question.
Yeah.
Regression, in the commonly used term, is that giving you partial correlations or semi-partial?
Semi-partial
It's giving you
correlation.
semi-partial.
The concept of semi-partial correlations. Okay, so cognition, is that sort of a biological, medical kind of a thing? Right? Any neurologist in the room? No, they would say yes. Shit. How about time spent at home? How are you going to classify that? Well, you said time spent. It's somebody over here said time spent at
You
home.
can put it along with medical, because it could be a surrogate for like functional status.
Okay, fine.
I think it goes with support too.
Yeah.
Well, let's think about that. You're talking
'Cause
about...
it's basically time spent independent in your home as opposed to a facility.
So what I might do is I might think about those things as kind of different, right? Because I might think about these things in green maybe as things that if I chose to, I could intervene on. I could intervene on somebody's pain. I could treat their comorbidities. I might treat their pain and comorbidities to increase their functional status, which should decrease the time spent with the doc, increase their depression, or decrease the depression, you know what I mean, and increase their cognition, right? From a medical perspective, right? I can either give them a drug or PT or something, right? Whereas support, I'm running out of colors here. Support and time spent at home, are you talking about psychosocial variables that are, they're psychosocial factors, but they're not demographic, not necessarily demographic, okay? Right? So now we're beginning to think about variables in a different way. Is that everything? Okay, and then we have seasonality, which I actually could choose to deliver my intervention in different seasons, right? It would be maybe kind of silly to deliver a seasonal affective disorder intervention, say in the summertime where it's nice, bright and shiny, everyone's getting the vitamins from being outside and so on and so forth. And I don't have another color, so I'm going to use this icky yellow. Another kind of variable. And then finally, we have the variable that I'm really interested in studying. That's the variable that I'm really interested in studying. So let's give names to these kinds of variables. And let's think of a strategy for answering a policy question. How might we think about these variables from a policy perspective? So green or purple are demography variables. And I think the next one we tackled was green, right? What do we want to call those? There's no wrong answers. If that makes you feel better. We can call it whatever you want.
Patient variables.
Patient, okay, patient variables. Patient VARs. And we said they were green. And then we had, what did we tackle next? red. Then we had psychosocial. Huh? Say that again? No, go ahead.
She said green was the health related.
Okay. I'll put that in parentheses. Health. Then we had yellow. What are we going to call yellow? Time. Calendar time. And then finally, dun, 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 treatment. What's the most important variable in these sets of variables?
Treatment.
Probably that one, all right? So I'm just going to label these. I'm just going to label these 1, 2, 3, and 4, 5. And what we want to maybe do is think about, okay, is there a logical sequence that I could enter these variables into the equation to residualize my y variable in subsequent regressions? So for example, let's take, what is the thing that is least important from a policy perspective? Demographics, because we can't do anything about it, right? We can't change that. People are however old they are. So the first thing I might do is I might say, okay, in the first step of my regressions in interpreting the data, the first thing I might do is step 1. I might regress y on demog yielding y prime, right? So y is no longer quality of life. It's quality of life with the demography variables removed from it. Yeah? That model is going to come up with an R squared, right? That model will have an R squared. And notice now I'm changing something. Before I was writing little r, now I'm writing capital R. We call this a multiple R squared. The interpretation is exactly the same. It's a correlation. Because instead, okay, let's take a step back here. Let's look at this equation. And I could rewrite this equation this way, right? That's a generalization of what we did on day 1. Right? So if you remember on day 1, we had this, and then we did this. Right? We did this, and then we generalized it to this. We're just going to generalize this. Right? So now we're going to have now I have several predictors, and just like I've been doing over here, I can do the same thing. I can say yi minus beta 0 right? It's the same concept. It's exactly the same thing. Right? It's exactly the same thing. Make sense? Okay, so this epsilon I, I'll write in parentheses, is what I'm now calling y prime. Single prime. Got it? Okay. What's the next least important, or what's the next most important variable after demography that I might want to control for next? But I might have some substantive interest in saying, okay, what is the effect of this variable? And you can mathematically think of a set of variables as a variable. Because as you see here, what's happening is that these variables combine into a single variable. And once you combine them into a single variable, then it becomes bivariate regression. That's all it is. So it really does get back to correlation and bivariate regression.
And it matters the order that you...
Yes.
Okay.
Yes, and that's good insight. Because what we're asking, eventually what we're going to ask is, the question that we really want to ask from a policy perspective is, after I've controlled for all of these things, after I've residualized Y from all of these things that I either can't control, things that I could control but I'm not interested in controlling, things that I could control and I might want to see what the effect of that is, what's the best I can do? So what will happen is that we'll come up with Y prime, 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 and we're going to correlate Y prime, 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 prime with treatment.
Does the order of those initial ones matter, or it just matters that treatment's last?
Well, this is what I'm trying to get at here, is if you're interested in asking the question, okay, can you as physicians affect patients' psychosocial things? Probably not, or at least in any significant way without heroic efforts, right? But you might want to know what the effect of psychosocial attributes are on the outcome after controlling for demography. So what you're telling is a story, right? You see where we're trying to go with this? Instead of saying what's the effect of treatment, blah, which you can do, you can go right to this. That's easy, but you haven't squeezed all of the information you can out of the data to tell a story. And that's what we try and do when we analyze data. Otherwise, this just becomes, mental masturbation, and no one's going to care. You have wasted a lot of your resources. I think of doing things this way, theory building this way, as going to the beach. You ever go to the beach and your towel gets soaking wet? Right? That's a pisser, isn't it? If I may.
You're right.
So what happens? The first time you squeeze the towel, what happens?
A lot of water.
Most of the water comes out, right? What happens on successive wringings, runs, whatever we want to call it? Less and less come out, right? So in a sense, that's what we're doing, is in this case, we're literally wringing variance out of our outcome. And we're saying, okay, now that I've wrung the variance out for this, which I can never control, what am I then interested in? In a stepwise, disciplined fashion, to be able to tell a story and answer questions that I'm interested in answering about my data. I'm trying to describe the world. What's going on in the world? Where can I have an effect? Where can't I have an effect? Okay, if I believe that I can't have an effect, then I'm not going to take credit for that. So I'm just going to wring it out of the towel. So if I can't take credit for that, I'm going to wring it out of the towel. And then tell successive stories. Yes, ma'am?
So can you tell if you get it wrong? Like if you go demography, then health, then psychosocial, but really
It should have been?
flipped.
Yeah.
Can you tell?
Well, there's no doing it wrong. There's your hypothesized view of the world. A hypothesized view of the world. What does that sound like? It's a model. Your model can be wrong, absolutely. Sure it can be. It's going to be, all models are wrong, right? What you have to do as a researcher is to be able to substantiate and provide rationale for why you did what you did. Right? And that is how we build theories. Because if we just go in and we just start looking at associations in the data, you've heard that called fishing or mining or whatever, you're just going to you'll find relationships, but they're meaningless. They're meaningless. They are hypothesis generating as opposed to hypothesis confirming. Whereas if you go into your study in a disciplined way and you've identified your list of variables that you're interested in, and then you've taken that second step and said, okay, does it make sense in the particular thing that I'm doing to break the variables out this way? And if I can, is there a hierarchy here such that I can tell an interesting story? Because it might be, you know what, once I get to this point, it depends, it might, after I control for all of these things, time, when I give the intervention or when I deliver the intervention, may have a massive effect on what's going on, as opposed to the intervention itself. So my response to that is it wrong? All of our models are wrong. There's a famous quote by George Box, who was a statistician. It says, all models are wrong. Some are more useful than others. So is it wrong? Yeah, it's wrong. Everything we do is wrong. Everything. So I'm going to encourage you, God forbid, to think. Right? And this throws a lot of my students at the graduate level when I say things like, I'm going to encourage you to think, and they're like, what? You mean I just can't take the data and cram it through the software? Oh, yeah, you can. Absolutely, you can. Interpret the data. To interpret the data, you have to have context. What's the context? It's your hypothesis. How do you interpret data without a hypothesis, without a theory, to give the results some context? You can't, otherwise it's just a number. It's like, did everybody read the book Hitchhiker's Guide to the Galaxy? That's a timeless book.
I know.
That's a timeless book. My references are getting older and older as I am getting older and older, right? And at the end, they built the mother of all computers, and she spit out the answer of what's the meaning of life, and the answer was 42. And everyone was like, the hell does that mean? They're like, I don't know, so I've built the son of the mother of computers, and in a million years' time, he will have the answer to that question. Right? So you need context. You as the human being need to provide context and rationale. Yes, ma'am?
Tim, if you do 1, 3, 2, 4, will you get the same y prime?
You'll get the same answer here.
Okay.
But the y primes will be different based on the order in which you enter things into the equation.
Okay, but right before you get to 5, you'll still have the same number.
Yes. Okay. Right. Yeah. So. Yeah.
So when you regress y onto demographics, don't you just end up with like yi equals b0 or beta 0 plus beta 1 times x1? Because you don't know the rest of that stuff yet, right?
You'll get everything except the epsilon.
And you just regress
y
onto the demographics?
Onto this. Yeah, you'll get, these x's represent the variables in demography.
Okay. Yeah, so this is a variable.
So then what I would do is at step 2, let's decide on the next thing what's the next group of variables that we would use to predict?
I guess time.
Time, fine. There's no wrong answer. Good, thank you for speaking up. What I would do is I would regress y prime on time.
So when we're deciding the order,
yeah,
conceptually, do you want to take out things that your treatment will least impact? Like your age, that's not going to change anything. Time, it may not vary as much, but your treatment might affect your social or health stuff.
No, what I'm asking you to do is think about what's the question you're asking.
Right.
I don't know what question you're asking.
I see.
That's why you need to take that difficult, and I'm not being mean. A lot of people they really do get thrown when I say, you have to think about this. You can't look up in a book and say, first I should enter this, and then I should enter. It's completely based on your research question.
Right. But in conceptually, like when you're trying to decide the order of the variables, are you trying to order them in a sense of like what your treatment is least impacting?
The way that I would generally approach this is I would address this in the order of things that I'm least interested in.
Order of things you're least interested in. Okay.
Right? But I know, or at least I hypothesize, they're going to be related to the outcome of interest and the variable of interest, the final variable of interest.
Okay.
Right? So what I'm encouraging you guys to do by thinking about the data this way is then, these become, you think about it, you guys are starting off your scholarly careers. What you have here are 4 papers, logically. What's the effect of these health variables on quality of life holding these things constant? Paper 1. Congress 1. Congress 2 is being held in Hawaii. What's the effect of psychosocial variables on quality of life after holding these things constant? Well, interesting question. Then you write in your discussion section. The next thing we should answer is, what is the effect of time? Right? This is how science works. Science doesn't work by finding the answer all at once. It's not how it works. Science works by taking, 5 steps forward, 4 steps back. 1 step forward, 2 steps back. It works in these little bitty incremental things, right? So what we're trying to do, oh, by the way, you could, if you're interested in this, in treatment, and you don't care about these things, you can just include everything in the goddamn equation and get your treatment effect. There's nothing wrong with that. Multiple regression will yield the same answer. But what I'm trying to express to you, holy crap, it's time. What I'm trying to express to you is that there's so much more information in the data that you haven't looked at.
Sometimes I think about what to do in this situation. So let's say your 5 is not treatment, but it's a health state. And that health state may cause other health states that you're trying to control for. So, when you're pulling those out and you're left with the effect of that final health state, it caused some of the other ones that you pulled out of the equation.
Sure.
So that's just a case of you have to figure out what the model is
right.
and what to control for.
Did I draw this for you? Let me screw this up. I draw this for you? All right, so here we had, I think, unemployment. And over here we had inflation. So when you're thinking, you believe that this health state causes these other things. Cause is a very, very strong, if I may use an adjective, very, very strong word in science.
Right.
What you may say is associated with. But if you want to know the effect of that health state controlling for these other things, and that's your question, then answer that question. But you also might say, okay, I know these other things that are important too. So I'm going to control for all these other things, and at step whatever, I want to look at the effect of these other health states on the outcome. What is the effect of that? Okay. Then in your final step, look at the effect of what is the effect of that final thing that you're interested in, which answers the question above and beyond all of those other things. What is the unique amount of variance? Or what is the unique association, or the incremental is a better word. What is the incremental variance, the incremental explanatory power of this variable? It's a different question. And getting people to succinctly define the question is really hard. It's a really hard thing to do because today we are so used to, typing something into Google or whatever and getting 10 gazillion answers. That's not how science works. Science works on a very specific question. And you design your study to answer that specific question. So we have this struggle between, generation X, Y, what the hell are we at now? Whatever generation we're in now, and this immediate gratification. So it's this struggle. But science works in a very plodding, methodical way. Because we could get an association between X and Y prime. But as we said before, it's not enough to show the relationship in science. We need to understand the relationship. How and why are these things related? So it's not good enough to be right. We have to be right for the right reasons in science. So, okay. So what I want to do on Tuesday or Thursday is I want to do an example of this by hand to show you that you get this. You've done all of this. You know how to do all of this. You really, really do. So we'll do it together by hand, and then I'll show you, we'll let the computer do it, and it does it, bing, and you'll be like,